All right, so this is lesson 22, and what we're going to be working on today is actually determining those intersections between three planes that we've been talking about. So what we focused on last time was all the possible scenarios that could occur, and we saw that there was 8 possible scenarios, but 5 of those involved planes that were parallel. Okay, which sort of made that a much easier problem. And then when you were dealing with 3 planes that were not parallel, well, there were 3 options. Okay, there's sort of the main one. Okay, when things work out nicely and there's exactly that one point of intersection, but you also have a scenario where there might be no solutions, and the scenario where there might be infinitely many solutions. In other words, where they intersect in a line. Okay, so if I take a look at this first question, what do you think the first thing I should be doing? What should be my first step when I'm given a system of equations? So in this case here, yes, these represent 3 planes, and we can think of it in terms of an intersection. But as I think I've alluded to, what's really going to be important is more this idea that it allows us to solve for 3 unknowns with these 3 linear equations. Okay, that's it. The first thing you should always do is take a quick look to see if any of the planes are parallel, because if they are, then your life is made much, much easier. Okay, but we take a look at this here and we see that none of the planes are parallel. Okay, so I called these linear equations, and you might sort of say, well, wait a minute, this doesn't represent a line. It represents a plane. Yeah, geometrically it's not linear, but algebraically it is linear. Okay, in other words, when we talk about being linear, we talk about a linear combination of the objects, in this case here, the variables. So this is a linear combination of the variables x, y, and z. Okay, there's no squares, there's no square roots, there's no cosines. It's a linear combination. Hence, this is considered a linear equation. All right. Now, in particular, this x, y, z could represent the components of a point in 3 space, but it doesn't have to. X could be the amount of money that you're investing in one account, y is the amount of money in another account, and z is the amount of money being invested in a third account. Okay, so the idea that while we're starting off geometrically, this will lead to a way to solve problems not involving anything to do with geometry. Okay, so this is something that seems kind of new, but what's been our take every time we try to start something new that doesn't look completely unfamiliar? What should be our strategy, at least a first try? So here we are solving 3 equations and 3 unknowns. Yeah, can we recycle some of the stuff that we've done before? And we already saw that with 2 equations and 3 unknowns. Okay, so one of the ways in which you solve linear equations would have been substitution. And there's an argument to be made that I could easily isolate this x, that z, that y, this y, that z. Okay, so there's certainly an argument to be made that we could work with substitution by first isolating a variable. But the idea is that that's not always going to be the case. Okay, so even though it might be a reasonable option in this particular circumstance, okay, we're going to stick with elimination. Okay, but what happens if I take 2 of these equations and I eliminate a variable? What am I left with? By and large, when I use 2 of these equations and I eliminate a variable, what am I still left with? Well, I think if I eliminate one variable, I actually think I might be left with, yeah, and that's the thing, is that you're still left with an equation that possesses 2 variables, okay? Now, when we were solving intersections of 2 planes, that wasn't surprising because we knew we were looking for something that was going to give infinitely many solutions. But here, presumably, we're going to look for something that might produce a single solution. But I kind of agree with the suggestion that let's just try doing it and let's see what happens, okay? So what I'm going to do is I'm going to work with equations 1 and 2. It doesn't really matter, but I'll eliminate these z's, okay? So if I want to eliminate these z's, I'll do 1 minus 2. Okay, now again, I'm not going to write this out every time, like the whole equation one on top of the other, but if you feel like, you're making errors, you might want to consider doing that, okay? But I'm going to try to do it without actually writing it out. So I'm going to do equation 1 minus equation 2. So x minus 2x is negative x, and of course, please make sure you're checking my algebra here. So I have 2y minus negative y, so 2y plus y, so plus 3y. Okay, z minus z, 0. That's what I was trying to accomplish. Okay, and 12 minus 5 is 7. Okay, now, when we were solving uh, for two planes, we would have, isolated one of these variables and then done a substitution. But remember, I'm not looking to produce necessarily the equation of a line. So I feel as though I might be able to go a little further. Okay. The problem is if I want to solve for exact values of x and y, what am I going to need in order to be able to solve for exact values of x and y? And this is something you know very well. There you go, is you're going to need a second equation. And that's the whole trick for solving this, is that you use two of these planes to produce one equation. So actually, Ali, I'm not going to go that route of isolating one of the variables. Is what I'm going to do is I'm going to try to produce another equation in x and y. And then we'll see what happens, okay? So what I'm going to do here now is I'm going to choose another pair of equations, okay? And, it could be, 1 and 3, 2 and 3. But the idea is I want to choose this other pair, but eliminate the same variable, okay? And that's the important, that's sometimes the error people make, is they use 2 and 3 and they eliminate the y. But that's of no use for me. What I want to do is create another equation in x and y. I don't want to create an equation that has x and z in it, okay? So let's go ahead and do that. So let's say I use equations 1 and 3. And again, I want to eliminate z. So what I'll do is I'll multiply equation 1 by 2, okay? And I'll leave equation 3 as is, okay? So I'll actually write this one out just so that we can see the work. So let me multiply equation 1 by 2. So what do we have? We have 2x plus 2y plus, whoops, there you go. So 4y plus 2z equals 24. And I'm going to keep equation 3 as it is. Okay, so what do we have? 3x plus y minus 2z equals 1. Okay, and here I'm going to add them together in order to eliminate the z. So what do we have? We have 2 plus 3 is 5x. Okay, 4 plus 1 is plus 5y. These eliminate as I hoped, and 24 plus 1 is 25. And look what I've managed to do. By combining these equations, which doesn't change the values of x, y, and z, because I'm just performing legal operations on these equations, look what I've done. I've created now an equation in x and y and another equation in x and y. So what can I now do with these two equations in x and y? Well, I've just created a new system of two equations in two unknowns. Exactly. I'm going to solve this equation the way I normally solve a system of two equations in two unknowns. Okay? So look what I've done is I've taken this question of solving three equations and three unknowns, and I've turned it into a system of two equations and two unknowns. And guess what? I know how to solve that already. I don't need to come up with some newfangled way of solving that. Now, by the way, can you sort of see something I can do that would be nice with this equation to make my life easier? Again, think legal operations. There you go. I'll divide both sides of the equation by 5. So this can be written as x plus y equals 5. And these are the two equations I'm now going to solve. I'll call this equation 4 because I don't want to, I've already used 1, 2, and 3, and I'll call this equation 5. And now I'm going to solve the system of equations 4 and 5. Okay? So here, It's even ready-made because I can just add them, so the x's eliminate. So I'll do 4 plus 5. Okay, so what do we have? Negative x plus x is 0. 3y plus y is 4y. And then here we have 7 plus 5 is 12. And look what we've determined, an exact value for y. Okay, now that I have this exact value, what can I do next? Don't think too hard.
Plug it in.
There you go. Plug it into one of these two equations to find the x value. So here, I'll use equation 5 here because that looks a little easier. And we have x plus y, which we now know is equal to 3. And there you go. X is equal to 2. And now that I know what x and y are equal to, what's the final step? There you go. Let's now take these two, input into any one of these three equations, and determine the z value. So it's looking like equation 1 might be the easier one. Okay, so what do we have? We have x, which is 2, plus 2 times y, which is 3, plus z is equal to 12, and so z is equal to, so what is it? 6 plus 2 is 8, 12 minus 8 is 4. And there's the solution to the system of equations. And what is the geometric interpretation? There you go. The interpretation is that these three planes intersect at the point 2, 3, 4. So planes intersect at 2, 3, 4. Okay? And so this is quite nice because in the end, all we're doing is adapting something that we've already done. Okay? So just to kind of, I don't know how, sometimes as we're just learning these new things, we don't sort of put them in the context of the fact that this has been a journey for you, because you got to think back in grades 7 and 8, you just started talking about this idea of representing a unknown number with a variable and learning how to manipulate these expressions with variables. And then you got to grade 8 and 9 and you learned to solve equations and that these equations could represent something geometric like a line. Then you went to grade 10 and you started talking about two lines and solving systems of equations. And now from there, you're carrying it forward, okay? Because in the end, this is all just a culmination of things that you've seen before, okay? So just to recap how we solve these things, okay? Step number 1, use two equations to eliminate one of the three variables. Use another pair of equations to eliminate the same variable. And that now leaves you with a system of two equations and two unknowns, which you solve as usual. And then once you have those two variables, you can now substitute back to find the third. Okay? And if we wanted to, we can even check. Let's check, I don't know, equation 3. That's the more complex one. So let's see, 3 times 2 is 6, plus 3 is 9, minus 2 times 4 is 8, is equal to 1. So 2, 3, 4 is definitely on that plane. And let's do number 2. 2 times 2 is 4, minus 3 is 1, plus 4 is equal to 5. And number 1, well, we checked that. That's what we use to determine z. Okay? So this is our strategy for determining the solution to a system of three equations and three unknowns when none of the equations are parallel to each other. Okay? So in this case here, you could do that if you want kind of a heads up. You might ask yourself, you know what? Hey, let me just check if the vectors are not coplanar. Would I actually do that? I don't think I would. The only time I would do it is if you know that you're only interested in when the planes intersect at a point. If you're not interested in the other two scenarios, then you could check it. But I wouldn't say for the most part that it's going to be worth your time doing that. Because in the end, the algebra will take you there. And if in the end you have to solve this thing anyways, you would have just wasted, whatever, a minute, 2 minutes checking whether they're coplanar or not. So you can, but more often than not, you're probably not going to bother doing so. Okay? Any questions on the strategy here? All right. So, but now that we've seen that this process of solving 2 equations and 2 unknowns extends nicely to 3 equations and 3 unknowns, where do we go next? Yeah. Why stop here? Okay. Why not consider that you could continue this with 4 equations and 4 unknowns, or 5 and 5 unknowns? Okay. You might be dealing with systems that have a lot more parameters than just 3. You might even, you might go crazy and think about, what does it mean to talk about, possibly infinite unknowns? For sure. Why stop there? Can you sort of see, though, that this is going to start getting to be a lot more writing once you start getting to 4 equations or 5 equations? Okay. So this is where you start to realize that this fairly nice, clean scenario is going to get a lot trickier, because then if you have 4 equations and 4 unknowns, doing that first, doing that first elimination just then brings you to 3 equations and 3 unknowns, and you would have to do that 3 times. So you can start to see that this would get very, very messy when you go beyond 3 equations. And so this is why we're going to look at an alternative way of solving these equations. It's not different, because you're essentially going to be doing the same things. It's the structure that's going to look a little different. Okay, and the motivation is that once you go beyond 3 equations and 3 unknowns, actually writing this whole process out starts to get quite tricky and quite long. All right, so what I'm going to say, let's do one more example together, and then I'm going to have you work on the other 2 yourselves. Okay, so step number 1, what's the first thing I do? Quick, let's go, quick. What's the first thing I got to look at before I write anything down? There you go. Are there any parallel planes? Okay, from here to there, I can see definitely not parallel, and then here, nope, no planes are parallel. Make sure you force yourself, because the last thing you want to do is start this whole process only to realize in the middle, oh, I just wasted my time. 2 of them are parallel and distinct. There was no point in doing any of this work. Okay, so I'm going to say here, let's, I don't know, let's isolate, let's eliminate x maybe in this one here. Okay, this x looks like it's pretty reasonable. Okay, so let's subtract 1 minus 2, 1 minus 2. Okay, and let's see what we have. We have x minus x is 0. Y minus negative y. So we have 2y. 2 minus negative 4. So plus 6z. Okay, equals 6 minus negative 2. 6 plus 2 is 8. Okay, make sure you're checking my arithmetic. Okay, so here's my equation 4. Okay, let me now use I don't know, what should we do here? Let's use 1 and 3, I guess. Okay, so let's do 3 times equation 1 and then minus equation 3. Whoops, I lost the chat here. Okay, so this one here, I'm going to try to do it without writing it out. So this is where I want to be really careful. So it's going to be 3x minus 3x is 0. 3y minus 5y is negative 2y. Okay, so 3 times 2 is 6z, minus 12z is minus 6z. And then here we have 3 times 6 is 18, minus 27 is negative 9. Okay, and there's, I'll call equation 5. So as before, exactly as I expect, by eliminating the same variable twice, I'm now ending up with two equations and two unknowns. So I can solve that here. So here I see, oh, 2y, negative 2y. So I just have to add them together. So equation 4 plus equation 5. By the way, really good idea to do what I'm doing, showing me exactly what operations you're performing. Because if you make a mistake and I have to go and try to figure it out, especially grading all this stuff online, I don't know how diligent I'm going to be. I'm just giving you a heads up. So really you want to make sure your communication is concise, but make sure it's clear. Okay, so 2y minus 2y, 0y. Okay, here what do we have? 6z minus 6z plus 0. 8 minus 9, negative 1. What's up with that? Well, let's see what this is telling us. Because in trying to solve this, I was making an assumption. I was assuming that there was an intersection to be found. And so I went through the procedure of trying to determine this intersection. And in doing that, I came to this, what we call a contradiction. Okay? Because try as you might, 0 is not equal to negative 1. It's never equal to negative 1. It never will be equal to negative 1. So what this tells us is that our original assumption that there was a solution to this system of equation must be wrong. Okay? So our only alternative here is that there's no solution to this system of equation. Okay? Now, can we, hey, we didn't find a solution. Can we have a geometric interpretation if it turns out that there was no solution? Can we figure out what the geometric interpretation? So one of the scenarios was that we had two parallel planes that were distinct and a third, but we realized it can't be because there were no parallel planes. But now I'm looking at some of the other scenarios and oh, wait a minute, there was one scenario where you had three non-parallel planes with no intersection. And that was, as people are bringing up, this idea of the triangular prism. Three planes that never none of them are parallel, and they never all intersect at the same point. Okay, so there's our geometric interpretation. Okay, because we've already established that there's no parallel planes, and the only one that's left that does not have a solution is the triangular prism. So here we can say no intersection, planes form a triangular prism. Okay, and there's our geometric interpretation. All right. So could I have, taken the scalar triple product? Presumably that would have given me 0, and it would have given me the heads up that this was one of the possible scenarios. Sure. But again, what's nice is that the algebra will always take you there. That the algebra is constructed so that if you're trying to do something which is not possible, a contradiction is going to be produced. Okay? So what I want you to do now is I want you to follow this system to work on the next two problems. I'll give you a heads up that one of them, because again, we kind of dealt with what happens with parallel planes last time, okay? So you'll notice here that there's no parallel planes, but remember that there's still a third possibility that we haven't seen yet. So we've seen the intersect at a point. We've seen the no intersection, the triangular prism. So presumably in one of these, you're going to come across the third option. And the question is how are you going to deal with it? So think about that when you're solving the problem. Okay. So let me give you, if you get stuck on any one of them, just move on to the next one. Okay. So try to get as far as you can. Let me give you, this might take a bit of time. Let me give you maybe 8 minutes to try to work on these. Okay. And get as far as you can. Okay. So we're back. Hopefully we're back through some of this here. So let's let's see what this is going to look like. So, by the way, you will notice that by and large, I'm giving fairly easy examples. At this point here, you know, when you're trying to solve a system of equations like this, you're much more likely to use a systems of equations calculator. Okay, so we're not going to hit you over the head with working with fractions and decimals too often. All right, so here I'm going to do what I normally do, number them so I can be very clear about my operations. And it really looks like working with x, eliminating x seems to be the way to go here. Okay, so if I do 1 minus 2, we have x minus x is 0, negative 3 minus 11 is negative 14. Okay, here we have negative 2 minus 5 is negative 7z. And here we have 9 minus negative 5, so it's going to be 14. All right. And so if I now try to use, say, 1 and 3, okay, so let's see, what do we have? We have 2 times equation 1, and I'm going to be subtracting equation 2. So again, like I said, if you feel like it's a good idea to write these out to avoid mistakes, strongly suggest you do that. Okay, so 2 minus 2 is 0. So this is going to be negative 6 minus 8 is negative 14y. And then here we've got negative 4 minus 6. Sorry, wait a minute. I think that's how this is a negative 4 minus 7. Sorry, we're not multiplying. So negative 4 minus 3 is negative 7. Negative 7z. And then here we've got 18 minus 4 is 14. And presumably this is where you ended up. Because if I now call this equation 4 and equation 5, and I subtract 4 minus 5, what ended up happening? What do we end up with when we subtract equation 4 from equation 5? Is you end up with 0 equals 0. Okay? Now, again, we assume that there was some x, y, and z's that are common to all 3 of these planes, and that turned out to give us this equality, which is always true. So what is the conclusion? So yeah, I'll get there in a second. So the first conclusion is that there must be infinitely many solutions. Okay. Now, having said that, because, so here what this implies, and again, this would have been like what you did in grade 10 and you ended up with 0 equals 0, or 5 equals 5, or 10 equals 10. It implies that there's infinitely many solutions. Okay. And because there's only one scenario in which they have infinitely many solutions where none of the planes are parallel, then it must be that they intersect in a line. Okay, that's great. Are we done? Can we move on? Sorry, any questions, or can we move on? Oh, yes, of course. This is where in class I would pretend to hit my forehead and say, yeah, oh my God, of course. We want to know exactly what that line is because we want to know what the possible solutions are. Okay? But now that we know that there's a plane, that there's a line of intersection, well, we probably want to do what we were doing before when we're determining a line of intersection. What was our strategy for determining a line of intersection? So what's the general strategy we use to determine the equation of the line that represents a line? There you go, is write two of the variables in terms of the third, okay? And the idea here is I've already simplified 2 of the equations, okay? So I might as well work with the one that I already have. So whether it's 4 or 5, doesn't matter, they're the same equation. So if I take equation 4, what does equation 4 allow me to do? It allows me to write one variable in terms of the other. Of course, what should I do before I go ahead and work with equation 4? Make my life a little easier since I can. I might as well simplify it. So equation 4 can be simplified if I divide by 7 as negative 2y minus z equals 2. Okay? And from here, it's very easy to isolate z in terms of y. So negative 2y minus 2. And so now I'm just going to do exactly what I did before, is go back to one of the other equations and write x. Write x in terms of y. Okay, so here I guess I'll pick equation 1. Okay, again, try to show exactly what you're using at every step. So what do we have? Equation 1 says x minus 3y minus 2 times z, which is negative 2y minus 2, is equal to 9. And so here we got x minus 3y. So this is going to be plus 4y, and this is going to be plus 4 equals 9. And so x is equal to, so this is negative 3 plus 4 is y. Bring that to the other side, negative y. And then 9 minus 4 is 5, so plus 5. And now we have the information to write down our solution. We'll let y be our parameter t. And so now we can write x equals negative t plus 5, y equals t, and z equals negative 2t minus 2. Okay? And if we wanted to, you know, if you're so inclined, you could also write this in, you can write this in vector form if you wanted. Okay, let's just do a bit of review. What represents the point here? Let's remind ourselves, might as well review how we can write this equation. So what would be the point on the line? Where do you look for the point on the line? You look at the constants. So 5, this is plus 0 minus 2, so this would be 5, 0, negative 2, plus t times, and the direction vectors given by the coefficients of t. So negative 1, 1, negative 2. Okay, and there you have it. So again, the algebra will take you where you need to go. It first took you to the fact that there would be infinitely many solutions, and then that same algebra that you performed allowed you to find the equation of the line. All right? So should quickly go through number 4. Any questions on this here before I move on to that? Okay. I don't know if you can hear, my neighbor's kids are having an outdoor dance party right now, so I'm not sure if you can hear that. All right, 2 and 3. So again, before I start this, you might sort of notice that I'm going to use x again. You know, even though here z would be just as good, okay? In fact, maybe eliminating z might be slightly easier because I only have to multiply this by 2 in each case. Whereas here I have to multiply by 2 and then I have to multiply by 3. Well, there's a reason why I'm choosing to work with this x here on top. And it's because it's going to lead us to this alternative way of solving these systems of equations. Okay, now I think I'll leave that for Thursday when we get to that. But this is going to be the question we start with. So I'm just going to ask you to, if you're writing this out, hopefully you are, keep this copy that you're working with, because the first question we do is likely going to be this one here, if I remember correctly, that we're going to look at an alternative way to solve these problems. All right, but for now, let's just kind of do what we're doing here. So 2 times 1 minus 2. Okay, so 2x minus 2x, 0. So negative 6 plus 5, negative y. Okay, negative 4 plus 1, negative 3. Okay, negative 18 minus 3, negative 21. So again, make sure you're keeping track of my algebra here. And then I'll use this one here to eliminate the negative 3x. So I'll do 3 times 1, okay, and this time plus equation 3. So 3x minus 3x, 0. Sorry, just lost the chat there. Okay, so where was I now? This is going to be negative 9 plus 6. Negative 9 plus 6 is negative 3y. And then here, this is going to be negative 6 plus 2, negative 4z equal to, where was I? 3 times, so negative 27 plus 8 is negative 27 plus 8 is negative 19, right? Check the algebra. Does that look good? Is there a mistake here?
I feel like, should it be negative 5z?
Yeah, there you go. I think there's a mistake here. Okay, folks, you need to be a little more on the ball there. I hope we're all paying attention. I know this is not the ideal, but I made the mistake, but you folks have to be more on the ball in finding this here. So here we had negative 4 minus 1. I'm subtracting here, so that's negative 5z. Yeah, good. That's right, Sonia. Okay, so come on, folks. Please, when I ask you to check, you got to be a little more on the ball there. All right, so nothing to simplify here. So I'll call this equation 4. I'll call this equation 5. And so here I'm going to have to do a little bit of work. I guess I'll multiply that by 3. So I'll do 3 times equation 4. So that gives me negative 3y minus 15z. And this is 3 times negative 21 is negative 63. Okay, and I'm going to subtract this. So this is going to give me 0. So negative 4 plus 15 is 11z. And since I already made one silly mistake, I'm not going to take a chance on making another one. So negative 19 plus 63 is 44. Okay, Gene, these things are all chosen to work out really nicely. So z is just equal to 4. Okay, so once I have that, I can go back to this equation and determine y. So negative y minus 5 times 4 is equal to negative 21. So negative y is equal to, this is going to be negative 21 plus 1. So that's going to be, negative 21 plus 20. So negative 1. So y equals 1. Again, please check my algebra. And then lastly, I guess I'm looking for x. So I'm going to go put it back in that first equation. So x minus 3 times y, which is 1, minus 2 times z, which is 4, is equal to negative 9. So x, so this is negative 3 minus 8 is negative 11. So plus 11. So x is equal to 2. Okay. So this is the solution to my system of equations, and the geometric interpretation is that the planes intersect at the point 2, 1, 4. Okay? So, one last recap of the algorithm here. Take 2 equations, eliminate a variable. Take another pair of equations, eliminate the same variable. Solve the resulting system of 2 equations and 2 unknowns. And once you have those 2 variables, you can then go substitute back into one of the full equations to solve for the third.